Welcome, everybody, and thank you for joining us to this edition of our Bick Gardner 1-hour web seminar. I'm coming to you from Bick Gardner's U.S. headquarters in sunny Columbia, Maryland, located right between Baltimore and Washington, D.C. And today's topic is color control and prediction of color stability. So hopefully you have all managed to connect to WebEx's audio. If you haven't, of course, you can't hear me right now, and nothing I say will matter anyway. So instead of explaining this slide, I'm going to give you a random dog fact. Did you know that dogs' noses are wet to help them pick up particles out of the air, which improves their sense of smell? And now you know. Your speaker today is me, Corey Cohen, Application Specialist with Bick Gardner USA since February 2011, and I specialize in customer education and technical training. So just some general information about today's web seminar. You have all been muted, so you can go ahead and talk to your cat or sip on your coffee. None of us can hear you. Please document any questions you may have that I have not answered by the end of the presentation into the chat function. We will have some time at the end of the presentation for a brief question and answer session. And yes, a PDF version of this presentation will be sent to all participants by email. Today's agenda includes how to measure color and gloss and what is the interaction between the two, what are digital standards and why are they beneficial, and what is fluorescence and how can it be measured with the Spectra 2 guide, as well as a discussion of quantification of fluorescent light and prediction of color fading with the new indices delta E fluorescence and delta E 0. So let us begin with our web seminar on color control and prediction of color stability. So color and gloss harmony are, of course, key criteria in the purchasing decision. Consumers like products that look good, and part of looking good is that all the different parts of the product match. So it's important when different parts come together in the final product, whether it's an automobile or an appliance like a refrigerator or oven or microwave like you're seeing here. It's important that all those parts look good together. But additionally, it's also important that the parts have good light fastness. So light fastness is how well a product will hold its color over time, how much or little the color will change. So this is also a key quality criteria. Not only because you don't want the color to change too much over time, you want it to continue looking good, but different parts that are produced and painted or colored and in different locations sometimes can fade differently. The color will change differently. And so even if the product looks good at the beginning, all the different parts appear to match when you first buy it, maybe a year, 2 years or more down the line, those parts will fade differently, and those parts, different parts will no longer match, and that's not a good thing. So first, we're going to talk a little bit about gloss. So gloss is just an observation of a surface at what we call the specular angle. This light source that's shining light on this glossy surface, and the light is going to, a certain amount of that light is going to bounce off at the opposite angle, which we refer to as the specular angle. So if we have this observer positioned at that specular angle, that observer will see a reflection of that light source, which on this glossy surface, we can see a representation of it to the right. We can see that it's a nice, crisp, clear image of that reflected light source. But now we're looking at a matte surface. M-A-T-T-E means low gloss, so this is a low gloss surface. And what that means is as the light shines on the surface, less of that light is going to reflect off at the specular angle, and more of it is going to reflect off at all different angles, which we call diffusions. The light is being diffused as it hits the surface, you're getting less specular reflection. And so the reflected image that the observer will see at that specular angle is going to be fuzzier and less distinct, as we can see from this image here. So here we have two painted panels, one painted black, one painted red. Both sides have the exact same coloring, the exact same pigmentation, but half of each panel was also coated in a glossy clear coat. And this has an effect on how we actually see the color of the surface. The glossy part is going to look darker and more saturated to us. I mean, the color will look more saturated, despite being the same pigmentation, the same colored material. So color, not just color, but gloss as well, can influence the overall visual impression of the surface. And so because of that, we have a couple different standard instrument geometries, beginning with the 45-0 geometry, so-called because the light source is hitting the sample at a 45-degree angle, and the light detector is positioned at a 0-degree angle or normal to the surface. So the light source is hitting the sample at a 45-degree angle, but you can also see that it's hitting it from all sides. So it's sort of a cone of light all hitting the sample at that same 45-degree angle. And this is what we refer to as circumferential illumination. And this is meant to mimic how we typically see things in everyday life. When we look at something, we don't typically look at it at the specular angle, because what you're going to see then is what we commonly refer to as glare. We don't want to see glare when we're looking at a magazine or a device screen or whatever. We want to see the color and the text or whatever it is we're supposed to be seeing on there. And so typically we'll look at objects at a diffuse angle, which is the same way that this 45-0 geometry is designed. And so with this geometry, differences in gloss and structure in the surface are going to lead to measured color differences. And of course, that circumferential illumination is meant to reduce the influence of directionality. So that just means that you can orient your spectrophotometer, your 45-0 spectrophotometer on the surface and take a measurement, and then you could turn it 90 degrees or 180 degrees, and you should get the same measurement due to that, that homogeneous circumferential illumination. So some typical applications for this geometry of color instrument would be comparison to a defined standard, batch-to-batch control, as well as harmonization of various materials and structures. So the next geometry is called sphere spin. Spin stands for specular included. We'll get into what exactly that means in a minute. So the way this geometry works, instead of illuminating the sample directly, the light source is now shining light onto the inside of what we call an integrating sphere. And this is just a hollow sphere where the inside is coated with a white diffusing coating. So that light is shined onto that coating and it bounces all around that sphere. And by the time that light hits the sample, it is diffused, just meaning that it's hitting the sample from all different directions. So instead of having a defined illumination, a defined direction of illumination, as with the 45-0, now this type of instrument uses a diffused light source. So some typical applications would be color matching, color strength development, and weathering studies. And in this case, with the sphere spin instrument, differences in gloss and structure do lead to measured color, do not lead to measured color differences. And then that brings us to our final geometry, the sphere specs instrument. Spec stands for specular excluded. And so this is exactly the same as the sphere spin instrument, except with the introduction of a gloss trap, and this removes the gloss reflection from getting to the detector. And the purpose for this is to make a sphere instrument measure more like a 45-0 instrument, where the color values you get will be influenced by the gloss or the structure in the surface. So this has pretty good correlation to 45-0 instruments on high gloss surfaces, but as the gloss goes down, so does the correlation between specs and 45-0 instruments. By the way, spin and specs are also sometimes referred to as SCI and SCE, specular component included or specular component excluded. They're the exact same thing. Spin is SCI and specs is SCE. So the reason for that diminishment of the correlation at lower gloss levels is due to the gloss trap not capturing all of the diffused light from the specular reflection. When there's too much diffusion, that gloss trap isn't capturing enough light to make it read like a 45-0. But at higher gloss levels in particular, in this case, differences in gloss and structure do lead to measured color differences, as with the 45-0 instrument. So here we go back to our example of those painted panels, and here we can see the measurements of the black painted panel, the glossy side versus the matte side. You can see the gloss values there at the top right. One has a very high gloss value of 91 gloss units. The other has a very low gloss value of 4 gloss units. And we can see how that influences the measured color values we get from these different geometries. So over here on the left, with these 45C0 geometry, C in this case just refers to the circumferential illumination. So with this instrument, when you measure one side against the other, the glossier side is going to be measured as being much darker, just as how we see it. So we can see here that the L value of the glossy side measurement is much, much lower than the L value of the matte side, just as how we're seeing it. The D8 specs geometry, D8, by the way, stands for diffuse light source and 8 degree at the position of the detector, so that's just another term for a sphere instrument. And so that D8 specs geometry is going to measure very similarly to that 45-0 geometry, and the glossy side will be measured as being much darker than the matte side. But then we look at the D8 spin geometry, the SCI geometry, and that geometry is going to ignore the surface effect. It will ignore that gloss or texture on the surface. It's really only measuring the pigmentation, which is the same for both sides. And so that sphere instrument, that spin instrument, is going to measure both sides as being essentially the same. And then we'll take a look at the red panel. So again, we can see that with the 45C0 geometry, the glossy side is being measured as somewhat darker than the matte side. The L value is lower. And we can also see that now that we're dealing with a chromatic color, the A and B, the chroma values are going to be different as well. The glossy side is actually going to have higher A and B values, more chroma, just as how we see it. Similarly with the D8 specs geometry, that's going to measure the color as we see it. The glossy side is darker and more chromatic. But then again, the D8 spin geometry is going to measure both sides as being the same because that instrument does not care about the surface gloss. It's only looking at the pigmentation, which again is the same. So our new Spectro 2 guide instrument can measure color and gloss in one. It does come in both geometries, or all 3 geometries, I should say. So it comes in a D8 sphere version that is capable of doing both spin and specs measurements. You can actually do them both at once, just one click, one measurement, and you get both sets of values. It also comes in the 45C0 geometry for measuring color as the eye sees it. It has a 12 millimeter illuminated area, with 8 millimeters of that being the actual measured area. And it does come with an actual built-in 60-degree gloss meter with an illuminated measurement area of 10 by 5 millimeters. So this is not a calculated gloss as some competitive instruments have. This is an actual built-in gloss meter with its own light source and detector, and you can expect the same excellent performance out of that 60-degree gloss measurement as you can out of our standalone microgloss meters. So here we see sort of the inside of the makeup of the 45C0 geometry. We have 6 white LEDs, so these instruments use LED light sources, and you can see they're equally spaced around the aperture to provide for that circumferential illumination. And of course, the built-in 60-degree gloss measurement, which you can see on the left and right side. One is the light source, the other is the detector. There we go. And so this is according to international standards such as ASTM, ISO, JIS, CN, pretty standard worldwide. And then here we have the D8, the sphere geometry. This again uses, it has 1 LED and it shines that light inside of the integrating sphere to provide that diffuse illumination. Again, it does have spin and specs mode built into 1 meter, and that same built-in 60-degree gloss meter. So next we're going to talk a bit about fluorescence. So first of all, what is fluorescence? So here we have, this is that little red dot is orbiting, that's an electron orbiting the nucleus of an atom or molecule, which is represented by that orange circle. And so what happens is a photon or a particle of light of a given wavelength will hit that electron, and if it is of the right wavelength, of the right energy, that electron can absorb the photon. It can absorb the energy, which causes it to jump up to a higher orbital. So now that electron has more energy, it's in an excited state, but electrons don't really like being in excited states. They want to go back to the ground state, that lower orbital. So it's very quickly going to give that energy back off in the form of heat and light. So it's going to create some heat, and it's going to create a new photon. But because of conservation of energy, we know that the amount of energy it emits in heat and light has to be the same as the amount of energy it absorbed. And what that means is, since some of that energy was converted to heat, the photon that it re-emits has to be lower energy than the one it absorbed. And for wavelengths of light, lower energy means longer wavelengths. So it's absorbing a photon, or it's absorbing light of a given wavelength and then re-emitting it at a higher wavelength. And this is what's referred to as Stokes shift. And so you can have UV energy absorbed, and that can be converted into or re-emitted into the blue, green, yellow, or red range. You can absorb, or a fluorescent material could absorb blue light and then re-emit it as green, yellow, or red, or it could absorb green and re-emit as yellow or red. The point is, it can only go from shorter wavelength to longer wavelength, never from longer to shorter. So the Spectra 2 guide is not only a color and gloss instrument, it actually has a built-in portable fluorimeter. And this is for the purpose of color stability prediction. So it detects fluorescent light excited in both the UV and the visible light range. You can quantify this fluorescent re-emission using a fluorescent slider built into our Smart Chart software, which is included with every instrument. And it can also calculate what the color data will look like after that fluorescence has decayed, which is important because fluorescent pigments, fluorescent materials do have a tendency to decay over time. They're not going to stay at the same level forever. They tend to degrade. And so both these instruments, the D8 and the 45.0 version of the Spectra 2 guide, come with this built-in fluorimeter. And this consists of monochromatic illumination to excite the fluorescent material, which consists of 12 LEDs to excite the material, ranging from 360 to 660 nanometers. So 2 of those LEDs emit light in the UV range, and the other 10 emit light in the visible light range. These are monochromatic LEDs, so they're emitting very narrow band wavelengths of light. And so this is what our fluorescence slider looks like in the Smart Chart software, and I'm going to go ahead and demonstrate that for you. So here I have some measurements. I'm in the Smart Lab portion of Smart Chart, and I've taken some measurements with my Spectra 2 Guide 450 device. I've measured a few different samples. We'll take a look at the first one, which was just a sheet of white paper. So as is common knowledge, paper producers often use what we call optical brighteners to make their paper look whiter. And these are actually fluorescing agents. So what it's doing is optical brighteners are causing fluorescence in the material. It's taking UV light that is inherently in sunlight, and most forms of light have some UV in it. So it's taking that UV light and it's absorbing it and re-emitting it as blue light. And that's going to cause the paper to look whiter and due to that fluorescence. So we can view that in Smart Chart by looking at this fluorescence slider, which I'll pop out here. So here we have up here each of the 12 narrowband LEDs that's used to excite the fluorescent material. You can see that it's currently set on 360 nanometers. So that means it's shining 360 nanometer light on the sample, and it's showing us the amount of light that is converted to longer wavelengths due to fluorescence. So we're not looking at the reflected light at 360 nanometers. We're just looking at the fluorescent light that has been re-emitted at longer wavelengths. So we can see the curve of that re-emitted light. So there's a significant amount of fluorescence here, and I can step through the different LEDs, the different wavelengths, to see what excited wavelengths are exciting the material most and causing the most fluorescence. So we can see there's significant fluorescence in this UV range up through 410. We're also getting some fluorescence, and then it's fading out as we get to the longer wavelengths. So most of this fluorescence is happening, the excitation is happening between about 360 and 400, 410, whatever, and that light is being re-emitted in the blue range here. Next, we'll take a look at these tennis balls. I measured a couple of tennis balls, which turns out are highly fluorescent. They have that sort of very brilliant yellowish green color to them. And the reason that color is so brilliant and so bright and so chromatic is due to fluorescence. And we can look at that here as well with these fluorescent curves. So I'll pop this out as well, and we can just step through, again, these different LEDs to see how that's affecting the fluorescence. So we can see that there's some fluorescence going on in the UV range. The re-emission looks like it's happening kind of in the green to yellow range, which makes sense for a tennis ball. And I can sort of step through and see where most of that fluorescence is happening. So it looks like it peaks at around an excitation wavelength of 460 nanometers, and then it dips down again. Back to our presentation. So in addition to being able to view those fluorescent curves, the Spectra 2 Guide also calculates new fluorescent indices, the delta E fluorescence and delta E zero values based on that fluorescent measurement with the fluorimeter in the instrument. So the delta E fluorescence value, in short, it indicates whether and how much fluorescent energy is emitted. And so what that actually is the original specimen as it is now with fluorescence compared to the specimen after, or the sample after that fluorescence has all degraded. Once those fluorescent pigments are no longer fluorescing, they've all broken down, there's no longer any fluorescence in the material. So it's the sample as it is now versus the sample as it will be once all the fluorescence is gone. And so this is not a difference measurement in the sense of standard versus sample. This is the standard as it is now versus the standard as it will be in the future, or the sample as it is now versus the sample as it will be in the future. That's the delta E fluorescence value. And then we have the delta E zero value, which calculates the estimated color difference after all the fluorescence has decayed. So this one is the difference between standard and sample, the estimated difference between the standard and sample once all the fluorescence is gone from both. And so just kind of an easier way to look at this, we have a standard, and we can measure that against the sample and then calculate the delta E, the overall color difference between the two. This is pretty standard colorimetry, but with the built-in fluorimeter and the Spectra 2 guide, we can now also calculate the delta E fluorescence value, which again is the standard as it is now versus the standard once all the fluorescence is gone. So it's telling us how much the color is going to change due to the fading of that fluorescence. And similarly for the sample, delta E fluorescence, sample as it is now versus sample as it will be in the future. And then if we take the color difference between the standard and sample after all the fluorescence is gone, that is the delta E zero value. So the delta E zero value can be calculated according to any chosen equation. It could be the standard delta E star value, which is just the distance in color space, in LEV color space, or you can choose one of the other color difference equations, such as delta E CMC 94 2000. And we'll go back to Smart Chart. And so we'll take a look again at that white paper. So you can see here the delta fluorescence value, 8.02. So this is telling us that once all the fluorescence is gone from this paper, the color will change by a magnitude of 8.02, according to the delta E star equation. But even more than that, we can actually take a look at the fluorescent components, and it will tell us not just the magnitude of the change, but where that change is actually happening, and the LAB value. So we can see that the L value is getting slightly darker by only 0.69. So that's maybe a little surprising that the lightness of the color isn't going to change very much. But so most of that change is going to happen in the A and D values. We can see that the DA value, the DA fluorescence value, is negative 2.26, which means that that paper is going to get just a little bit greener as it ages. But most of that change is happening with the B value. The DB fluorescence value is 7.67. So this paper is going to get significantly yellower as it ages, which makes sense intuitively if we think about, taking a piece of white paper and leaving it out and leaving it exposed to light. We know that older paper looks yellower, so that matches up with what we know. So then again, we'll take a look at these two tennis balls, and we can see that the amount of fluorescence in these tennis balls is much, much more than in that paper. So the delta E fluorescent values are around 54, 55. So the magnitude, the overall magnitude of that color change is going to be just massive once all the fluorescence has faded from those tennis balls. Then again, we can look at those individual components, the DL, DA, DB. So those tennis balls are going to get significantly darker with time, about 13 units. But again, most of that change is happening in the chroma values, the A and the B. So the A value is going to get much, much higher. So after the fluorescence fades, the tennis balls will look much, much redder, or since they are actually in the green direction, we can see from the A value that the A value of the sample as it is now is very, very negative. It would be more appropriate to say that the color is going to get much less green. And for the DB value, again, that's where most of this color change is happening. So the tennis ball starts out very, very yellow with a B value of 90. Remember, positive B is yellow. So we would say that the the tennis balls are going to get much less yellow after the fluorescence has faded. And back one more time to our presentation. So the Spectra 2 guide also has a visual and acoustic signal to indicate when there's fluorescence in the standard or sample that's currently being measured. So it has a blue status LED to indicate when fluorescence is detected, and this happens when the emitted energy is more than 1% of the excited energy. So when at least 1% of the light in those monochromatic LEDs, or any one of the monochromatic LEDs, if more than 1% is shifted to a longer wavelength, that blue light will light up to tell you, hey, there's fluorescence in this material. And similarly, we have a pink status LED, which indicates that the amount of fluorescence in the material has exceeded the defined limit. So this means that the difference between the fluorescent color, the color as it is now, versus the color as it's predicted to be once the fluorescence is gone, if that difference is more than 1/3 of the tolerance, this pink light will light up to tell you that the fluorescence has exceeded that defined limit, and these tolerances can be customized in the software. So now we're going to talk about digital standards. So typically, or traditionally, I should say, the way that this is done is that when you have a global color management system, meaning you have some sort of headquarters location, and then you have lots of different production plants and or suppliers that are producing a particular color, typically that headquarters is going to produce a master color standard. So this is a physical standard, usually a painted panel or maybe a plastic piece or something, and that's going to be the worldwide target color. That's the color that they want every production plant, every supplier to aim for when producing a certain color. And so what will happen is, after that master standard has been produced, the headquarters will then produce a number of working standards to distribute to each of those production plants and suppliers so that they can measure that working standard with their own instrument in order to do color checks. So some of the issues with this type of system is that the working standards can differ from each other. So you have the master standard, then you try to reproduce working standards, but of course you're never going to be able to reproduce that color exactly. So already, even in the beginning, those working standards are going to differ somewhat from that master standard. And then when each individual plant measures that standard with their color instrument, there could be some operator influence in that measurement and or inter-instrument variation. So if the different instruments, even if they're the same exact type of instrument, they're typically going to each measure somewhat differently, and so that's going to introduce a source of error as well. And so this leads to the practical consequence of the question, is this a real measured color difference, or is this just due to these sources of error? And so in these cases, visual color approval becomes much more significant, which of course is rather subjective. So not a perfect system. So the benefit of digital standards is that you have one binding reference. You have the plants and suppliers working off the same master panel produced by that headquarters. You have one instrument that has measured that standard, and then it can be distributed electronically or digitally to all the different plants that need them, so that everybody's working off of the same standard. And in order to do that, what you need is an instrument with excellent inter-instrument agreement, such as the Spectra 2 guide. So here's just some examples of that. These are a range of colors as measured with several different Spectra 2 guide instruments, and you can see that the clustering is very, very tight. The inter-instrument agreement is excellent, just meaning that when you measure the same color with all of these different instruments of the same type, you're going to get the same values to within a very, very tight tolerance. You can see the clustering is very tight here. So here we're showing you a few neutral colors, a few different grays with different lightnesses, and then here we have some chromatic colors. And so that, again, that clustering is very, very tight. The inter-instrument agreement is very, very good, which allows for the use of those digital standards. And this is largely due to the LED technology that we use in our instruments. We have been using LEDs for a long, long time. We've gotten very good at it. And so this guarantees outstanding performance in the instrument. We're so confident of this light source. LEDs are so stable that we give them a 10-year warranty on the light source. All of our instruments that use LED light sources, which I believe at this point is all of them, we give a 10-year warranty with them all. And it's not because we enjoy replacing that light source for free. It's just that those light sources never really need replacement. This leads to great repeatability, both short and long-term. Repeatability is just if you take a single instrument and measure the same sample over and over again, how close will those measured values match to each other? You want to get the same thing over time. Provides homogeneous illumination, and it is very temperature stable from about 10 degrees to 40 degrees Celsius, which is 50 to 104 degrees Fahrenheit. This provides excellent inter-instrument agreement, which allows for digital standards. So digital standards bring the complete supply chain on target. You have one binding reference, so rather than having to produce a number of working standards to physically distribute that are typically going to differ from each other, even just by a little bit, you have one standard that all the plants and all the suppliers are working off of. And this minimizes error sources because those electronic standards, the digital standards, take the place of those certified master standards. And again, only instruments with excellent accuracy between instruments allow for the usage of digital standards. So these instruments, as mentioned, come with that smart chart software that I've been showing you. This is to analyze color harmony and stability. It comes with, there are two modules for you to choose from. One is Smart Lab. This is designed for R&D laboratories and testing labs and things like that. This allows for online measurement as well as memory transfer. If you take readings from the instrument and save them in the instrument itself, you can then transfer it to Smart Lab. It provides data analysis in all your favorite color systems with scatter and line graphs, as well as that color stability check with the fluorescence slider, as well as those fluorescent indices that you saw. And then we also have Smart Process, which is designed for production plants that are going to be measuring large amounts of data and will typically do the same types of measurements in the same order every single day or every single week. So this provides standardized quality control, a sampling process with digital standards defined in organizers, and you can save the data in SDF databases or SQL databases. And so you can create as many of those databases as you want. They can hold a huge amount of data. And it also provides comprehensive data analysis with easy filtering and statistical analysis. So one of the big benefits of Smart Process is that you can sort of standardize the labeling, or what we call parameters, of the measurements. You can apply different labels to them, and then once you have a large amount of data to sift through, you can very easily filter it and see what data you want to see exactly the way you want to see it. So once again, we will go back to Smart Chart. This is the Smart Lab portion for the Spectra 2 guide. And so suppose I now want to see difference values. I want to see the difference between tennis ball 1 and tennis ball 2. So what I can do is I can right-click on tennis ball 1, and then select Copy as New Standard. And so in here, it just created a new standard out of the data I had measured with tennis ball 1. And so I can actually change, let's go ahead and change this name. I'll call it tennis ball standard. And what I can do then is I can actually copy this sample and paste it down here in order to see the difference between this tennis ball standard, which again was tennis ball 1, the difference between that and tennis ball 2, which we are seeing over here. So we can see by the color difference values that these two are very, very close together, which makes sense because I got them out of the same bag. This is the same batch of tennis balls. So the DE is fairly small, the DL, the ADB, they're all fairly small. Remember that these delta E fluorescence values that you're seeing over here to the right, these are, that's the sample as it is now compared to the sample as it will be. So this is not a difference between sample and standard, these values on the right. These are just the tennis ball 2 now compared to tennis ball 2 once all the fluorescence is gone. So that's why you're seeing such massive values, even though these two tennis balls are virtually the same color. And then so what I can do, so now I've decided that this tennis ball standard, this is what I want to use as my master standard. This is what I want all of the tennis balls we produce or any of our suppliers produce. We want them all to match this one standard. So what I can do is then right-click on this standard, save it in the standard database, and then I can go to my standard management section, and I see that that tennis ball standard is here, so I can adjust any of the values or any of the settings that I want. Not the values, you can't adjust the measured values, but you can adjust the settings. You can add any indices, you can add gloss if you want to, you can add any of the specialized indices. Maybe I want to add a yellowness index for measurement. So I can adjust these settings as I want, and then I can go ahead and load this standard into my Spectra 2 guide and go ahead and take pass-fail measurements or color difference measurements with this standard. But the other thing I can do, I can also designate this standard as a master standard, and I can export this standard as an XML file. So it's a very small file, which I can then take and email or transfer via USB stick or whatever your preferred method is. I can distribute that one file to all of the plants or suppliers that also have a Spectra 2 guide and are using SmartChart. And they can take this exact same standard into their instrument. They can load it into their instrument and use it for difference measurements and pass-fail as well. So let's go ahead and pretend that I'm a supplier now, and I've been sent this tennis ball standard, so I can just go ahead and import that. And now I have that tennis ball standard as well, and I can go ahead and load it into my instrument for measurement. Okay, back to our presentation, almost done now. So the Spectra 2 guide, again, it has color, 60-degree gloss, and a built-in fluorimeter in one instrument. It is also a very modern device with some cool new features. It has a balanced, excuse me, a balanced and upfront design with a large color touchscreen. So operation is very easy, you know, similar to using an app on your phone. It has that large color display, which makes the values very easy to read. One of my favorite functions is the new live preview function. So this instrument actually has a camera built into it that looks down directly through the aperture opening. So you can activate that camera to see exactly what the instrument is resting on, exactly what is going to be measured. So that can be used to, if maybe you have a panel that needs to be measured or a part that needs to be measured, and maybe it's a little scratched up, or you know, somebody put a big fingerprint on one part of it and you want to make sure that you get a nice clean color measurement, you can use that preview function, that camera, to make sure that you get a nice clean area to measure. It can also be used if you have very, very small samples, if you have maybe a sample that's not much bigger than the aperture opening itself. You can use that preview camera to make sure that the Spectra 2 guide is perfectly centered on that small sample to make sure you're getting a good measurement. As discussed, it uses smart, high-tech LEDs with peak performance for those digital standards. And it has data analysis with Smart Chart included. And you can connect to that with a USB connection, either directly to the instrument itself or through a docking station, which is included. Or you can actually connect to the software via Wi-Fi. And here's the full line of our Spectra instruments, Spectra Guide instruments, beginning with the basic model, the old standby, the Spectra Guide. This has a reproducibility of 0.2, excellent reproducibility, but not tight enough, we would say, to use digital standards with. But this unit does also come with that built-in 60-degree gloss meter, and again, you can expect the same excellent performance out of those gloss measurements as you can from our standalone microgloss meters. And it includes a simple spreadsheet program for downloading data and doing some simple QC analysis. That's called our EasyLink software. And that, again, is included. Going up from there, we have our Spectra 2 Go model. This model has the tighter reproducibility. Reproducibility is just another word for inter-instrument agreement, by the way. And so that reproducibility is 0.1 delta E94, and so that allows, it's tight enough to allow for the use of digital standards. So this model also comes with the 60-degree gloss meter and includes the Smart Chart software, but this model, the Spectra 2 Go, is only for measuring non-fluorescent colors. This model does not have that built-in fluorimeter that we've been discussing. Going up from there, we have the Spectra 2 Guide instrument, and that is the one with the built-in fluorimeter. So this has the same excellent reproducibility that allows for digital standards as the Spectra 2 Go. It has that same built-in 60-degree gloss meter, but this is the one that can give you those fluorescent sliders that can show you the fluorescent curves, as well as calculate the new fluorescent indices, the delta E fluorescence and the delta E 0. And again, the Smart Chart software is included. So it's not an additional purchase. You don't have to pay extra for the software. It is included with every instrument. And then next to that, we have our top performing device, the Spectra 2 Guide Pro. And this has excellent reproducibility as well, allowing for digital standards. Also has that built-in gloss meter and the fluorescence detection. But this unit in particular is the specialized unit for measuring jetness. Now, jetness, real quick, is just a measure of how black is your black. So if that's important to your product, to make sure it's as dark or as black as possible, what you need is to perform jetness measurements. And the difficulty with jetness measurement is that by its very nature, because you're measuring black colors, the reflectance is very, very low. And so that sort of amplifies the uncertainty of the measurement. That amplifies the noise to signal ratio. And so what you need in order to measure jetness is you need a very, very precise instrument that's going to have very, very tight repeatability and reproducibility, especially at that very low reflectance level. So that's what the Spectra 2 Guide Pro is for. And again, this unit also comes with the Smart Chart software. So that wraps up our technical presentation, just a few cleanup tasks. Here is the technical service team for Bic Gardner, including my colleagues over at our German headquarters, as well as those of us here in the US. So you can see that we have listed our contact info here, and that is to encourage you to please reach out to us. You don't have to wait for one of these events to have your questions answered. We'd love to speak with you directly and discuss your application at any time, so feel free to reach out to any one of us. Our next 1-hour web seminar will be on March 10th and 11th. and that is on measurement of effect colors. This is not a two-part web seminar. It's the same web seminar on both days. When we are allowed to travel again, when we can safely do so, we do like to give on-site seminars. So if you have a desire or a need to have some intensive education specifically customized to your needs, we can do that. We can go to your site. We can customize a presentation specifically to suit you, whatever you want to learn about, whether it's color or gloss or surface structure or even physical test instruments. We can customize to meet your needs, and we can bring our instruments with us so you can try them out. We have a new website at byk-instruments.com. Check it out. And we have a number of instructional videos available on YouTube. You can see those at youtube.com/user/vicvideo. And finally, once it is again safe to travel, we would love to host you at one of our sites. On the top left there, you can see our German headquarters, our main production and R&D site. So my colleagues would love to have you there and show you around. They also produce this stuff in Germany called beer. I don't know if you've ever heard of it. They've been doing it for a long, long time and have nearly perfected the process. And over there on the bottom left, that is our U.S. headquarters located in Columbia, Maryland. We'd love to have you in as well to show around our facility and our service lab. It's located right near Washington, D.C., so plenty to see and do there at your own risk, of course. Also, we have crabs, but in a good way. We do like our crabs here in Maryland, so if you do happen to stop by, I highly encourage you to get some crab cakes. We also make beer as well. We have stolen all of the Germans' beer-making secrets and actually further perfected it, so the beer you can get here is actually even better than what you can get in Germany. So that's it for my presentation. Hopefully this was beneficial to you. I will now take some questions. Just give me a minute to look at the chat box. Can I get a presentation after? Yes, the presentation will automatically be sent out to all of you in PDF format. So someone is asking, for digital standards, can the headquarters have the Spectra 2 Profiler, which is one of our new instruments that measures surface structure, to match surface structure on different textured surfaces? So the question is, can the headquarters have the Profiler instrument and the supplier have the Spectra 2 Guide? I believe that would be okay. Some considerations to think about, though. The Spectra 2 Profiler does not have the built-in fluorimeter, so if you're dealing with fluorescent colors, you would not want to use that combination. Also, the Spectra 2 Profiler has a larger aperture, so the measurements might be just slightly different due to that, as well as the Spectra 2 Profiler only comes in a 45-0 version, so you would only want to match it up with a 45-0 Spectra 2 guide. Will UV protector in resins affect the fluorescence on a sample? So I'm not too familiar with UV protectors. I'd imagine that is some sort of coating or chemical that prevents the fluorescence from fading. So I can't say whether it would have any effect on the fluorescence itself. I'd imagine that is not its purpose, that its purpose is just to preserve the fluorescence. So assuming that's true, then no, that UV protector wouldn't have an effect on the fluorescence level. I'm sorry, Alessandra, I don't understand exactly what you're asking. Could you try to clarify or maybe just contact me after the presentation? I'd be happy to speak with you directly. Okay, the light source LED, what is the reflective power distribution curve? Daylight, does the software convert it to the desired light source? So it does not conform exactly to daylight. No spectrophotometer does. It's just an even white light source with a fairly even distribution of all the different wavelengths. This is how spectrophotometers are designed, have a fairly even distribution of all the wavelengths, and then all the different illuminants that you can select if you want to see your color numbers, what they look like under daylight illuminance or fluorescent illuminance or incandescent. That is calculation in the software. So the physical light source in the instrument doesn't actually have to match any specific illuminant. It just measures a reflectance curve, and that data is used to calculate what those colors look like under all the different illuminants. What about accuracy on irregular surfaces? Okay, so typically on irregular surfaces or textured surfaces, the 45-0 instrument, you could get different readings depending on what spot you're placing it on. Different spots are going to have slightly different textures. You're going to be hitting different, peaks and valleys depending on exactly how it's positioned. So if you are measuring a textured or structured surface or irregular surface with a 45-0, I would recommend doing a high number of averages to make sure you get a good color reading across the surface. If you really want regular measurement, you really just want to measure the pigmentation of the surface, sphere would give more consistent measurement. But even then, I'd probably recommend doing some averaging on a irregular or textured surface. How is the difference to BICMAC eye? Okay, interesting question. So the BICMAC eye is our multi-angle color instrument for measuring effect pigments or materials with effect pigments in them, where the appearance can change depending on the observation angle. So typically the solid colors, colors without effect pigments in them, the appearance is going to be pretty much the same at all the diffuse angles, whereas with colors that have effect pigments on them, they won't. So the BICMAC eye, typically if you're using, first of all, the BICMAC eye has a directional light source, so it's going to be more akin to the 45-0 geometry of a solid color instrument rather than the sphere. So if you're comparing 45-0 to the BICMAC, typically they will match fairly well at a 45-degree angle. If you select the 45-degree measurement angle of the BICMAC. One consideration, though, is that the Spectra 2 guide and the Spectra guide have circumferential illumination, whereas the BICMAC does not. And that's by design because with effect pigments, the orientation of the instrument on the surface and the orientation of the light source and the observer is going to have an effect on how we see the color. So just know that you might get some differences just due to the fact that the BICMAC has a truly directional light source, whereas the 45-0 uses circumferential illumination. What will be the best practice to convert a painted master into a resin or plastic working standard? Really all I can say about that is that you would certainly want to use a 45-0 instrument because you're likely to get gloss differences between a painted panel and a plastic panel or a plastic piece. And so if you want them to look as close as possible to each other, you want to compare them using the instrument that measures as our eye sees it, which is the 45-0. Does the fact that it is portable affect the accuracy of the results? No, I would say that The Spectre 2 guide, the portable instrument, has better precision, better reproducibility and repeatability than probably most of the benchtop instruments on the market. One consideration, of course, is positioning, or making sure that the instrument isn't moved during measurement, but it actually has sensors built into it that will tell you if the instrument is moved during measurement, and if maybe you need to repeat the measurement. So it is very, very precise, very accurate, and it does have safeguards built in that will prevent you from taking faulty measurements. What is the smallest object size you can measure with your instrument? So the spot size that's measured with the Spectre 2 guide. So for color, it's an 8mm circle. For gloss, that 60-degree built-in gloss meter, it's 10 by 5mm. So I'd say you'd want at least like a 10mm square or 10mm circle. Ideally, slightly bigger than that, just so the positioning of the sample isn't a huge issue. But again, you can use that preview camera, which will help you position it on very small samples. Yes, the recorded video of this webinar will be available on our website for, I believe, a month. So you can just go to the same place on our website that you went to register for this web seminar, and you'll be able to access the recording there. And if you have any colleagues that would like to view it, all they need to do is register, and they'll be able to access the recording as well. For liquid samples, we do have an instrument that can measure transparent liquid color. Currently, we don't have one that can measure opaque liquids, but we will in the very near future, so keep a lookout for that. It looks like it is past 11 now, and we have reached the end of our questions, so I will go ahead and conclude today's web seminar. Thank you all for coming. I hope it was beneficial to all of you. I hope you'll join us for the next one. Have a great day, everyone.